Okay, let me start over. So I present an overview of searches for new physics at the LHC. And we start this overview at a point where the previous talk has ended. So we asked what comes after the Higgs discovery. We have this new particle that completes the standard model, but it raises new questions at the same time. Its mass is unnaturally low, given that it is susceptible to corrections which would arise from heavier particles that are yet unknown. Also, we have seen in the previous talk there's this hierarchy of its fermion couplings. We don't know where that comes from. This should be addressed by new physics, and this argument of naturalness suggests to us that this enters at an energy scale not too far from the electroweak scale. But we are in a new situation now, contrary to the past, where the standard model predicted discovery for us, like the WZ, the TOP, and the Higgs. We don't have prospect as clear as that anymore. Normal no-lose theorem, and in this situation, it's of course great to have a discovery machine, the Large Hadron Collider, and we use it to conduct a broad search program where we cover as many signatures as possible. Certainly, at least by the time of the start of data taking, supersymmetry was the most favored scenario beyond the standard model. Here, new particles are introduced. They would provide corrections to the Higgs mass that stabilize it at the electroweak scale. If these supersymmetry particles are of masses on the order of a TeV, the primary experimental target are strongly interacting particles like the gluinos produced in pairs, and then they decay, for instance, to give hadronic jets, and the weakly interacting neutralinos. If these are stable, then they cause missing transverse energy or missing ET. Also, in that case, there would be an interesting candidate to explain the observed dark matter in the universe. This was a projected discovery early on, as seen here in the Atlas letter of intent. This is a missing ET spectrum for an envisioned supersymmetry signal compared to the background. So we were hoping for this, and what we've got was this. This is a missing ET spectrum seen by Atlas in the 2010 dataset. There are a couple of backgrounds, like the production of jets together with the Z boson that decays to neutrinos, which causes missing ET. The sum of the backgrounds describes the data within uncertainties, and there's no sign of supersymmetry. Now, due to the unprecedented center of mass energy of 7 TeV, this resulted in a huge increase of exclusion limits on supersymmetry, shown here in a model popular at the time, where the Atlas limits then in red go way beyond what has been excluded before by LEP and the Tevatron. We make another jump in time to the present, to the much larger 1-2 data set with 13 TeV collisions. There are still no signs for such gluinos. This sets limits on their mass, depending on the neutralino mass, which go way beyond what has been excluded with the early data, and now reaches up to 2.3 eV in the neutralino in the gluino mass. With gluinos absent, we look for squarks next, in particular the top quark partner, or the STOP, which would contribute most to the protection of the Higgs mass, so to say, if its own mass is on the order of a TeV, so hence in our reach. Now, in the bulk of the parameter space, the pair production of stop quarks via strong interactions results in final states that have top quark pairs and missing ET due to the neutralinos. This is a comparison here of the cross-section of the signal, depending on stop quark mass, compared with the background cross-section, that's top quark pair production. We've seen it in the previous talk. Now for the stop quark mass close to the top quark mass, we have very similar, essentially the same cross-sections, just the same process with different spins then. But for a higher stop quark mass, the cross-section drops considerably. We need then missing ET. This is the distinguishing feature to identify still the signal. Now, missing ET reconstruction involves the whole detector. So what the plot means experimentally is that we must have a very good understanding of our detectors to become sensitive to these stop quarks. We achieve this, and hence our sensitivity reaches up to 1.3 TeV in the stop mass, where the signal is 6 orders of magnitude less abundant than the background. Still, there are no signs of supersymmetry, and this excludes parameter space, given here in this plane of the stop and the neutralino mass. It rules out a large fraction of the parameter space that was suggested to us by naturalness. There have been many more searches performed for supersymmetry. Still, there are no signs for it in our data. In that situation, we need to consider other scenarios of new physics. Now, while supersymmetry is something that addresses many questions at the same time, an alternative would be to address one question at a time, say dark matter, about which we know from astrophysics that it's there. Unfortunately, we only know one more thing about it, which is that it's only very weakly interacting. If this is due to new weak interactions, new very heavy mediators that would also involve quark couplings, we could actually produce the dark matter like this in our collider. This would be pair production then of dark matter, and we would need to have in addition radiation, particularly due to strong interactions, that gives the jet, and then we have a jet in the detector missing transverse energy due to the dark matter. It's very similar to what we have seen from UA1 and UA2 before. Still, of course, time has developed. Now here in this monojet search by Atlas, we have the missing T spectrum with much more data in there compared to what we've seen from UA1 and UA2. There are a couple of backgrounds, in particular, again, jets together with the Z boson, where the Z boson decays to neutrinos. That's here in red. It's worth noting also that nowadays we have particularly high accuracy from theory, and that comes in here. This is necessary because the statistical uncertainties with such a large data set are very low. Hence, we need also small theory uncertainties to still make good use of the data. We have this. And still there's no excess here at large values of the missing ET. And this results in exclusion limits on the mediator mass and on the dark matter mass. So we have this triangle, where is it? Triangle of exclusion here. We can compare this with direct searches for dark matter. Those are low temperature experiments that look for elastic scattering of dark matter and nuclei. We have the plane of the elastic scattering cross-section and the dark matter here. We find again the triangle of exclusion from LHC there. And we compare it with the direct search exclusion. They are sensitive at dark matter masses close to the nucleus mass. That's because it's elastic scattering, about 100 GeV for xenon, but not at lower masses where the collider is sensitive. So the two approaches are complementary to each other. What we also see here is that in this model we should also expect quarks in the final state. We search for this as well. As is shown here, we have events selected that come with pairs of highly energetic jets, and then we consider their invariant mass spectrum. Here, the background from strong interactions is deeply falling, and we look for peaks on top of it. It's interesting to note that the lower threshold here is actually predetermined by the bandwidth of the data acquisition system, about 2 gigabytes per second. Now, to still make good use of the data here, lower the threshold, what's something that's called the data scouting stream is introduced. This technique, jets are stored on tape only in the way in which they're handled in the trigger system, storing in particular only calorimeter information. This reduces the event size, and hence a higher recording rate can be allowed. This is used to lower the threshold and hence increase the range of the search. So there are no peaks found here, and this excludes such new mediators for recouplings across the probe mass range. This is an example where we see that searches are not only about reaching higher energies, but also reaching higher intensities. That's also the case in this search here from Atlas, about lepton flavor violation. In fact, the LHC in 1.2 has produced more Z bosons than LEP. So to say, 8 billion per experiment compared to 4.5 million. This allows stringent tests of the standard model. Atlas looks here for Z decays into two charged leptons of different flavor. This is not allowed in the standard model, so it's an interesting test for new physics. There are backgrounds, in particular the decay of Z bosons to 2 tau leptons that looks very similar to this signal. Hence, a neural network is used here. This is a complex nonlinear functions derived from simulations and applied to the data to distinguish a potential signal from the background. We obtain upper limits on the branching ratio of such rare decays, which are as low as 3 out of 10 million decays in the electron muon case. This is 2 to 5 times more sensitive than what has been achieved with the LEP data. Talking about lepton flavor violation, this is actually the hot topic these days. This is because tension with the standard model is seen also by LHCb, we must say, looking at the next talk already, in B-meson decays, semi-leptonic B-meson decays. What's interesting for us to note here in this talk is that one of the popular explanations for this involves leptoquarks, new particles that would contribute to this decay here into quarks and leptons. They would need to be of a TeV scale mass to fit the size of the observed effect and have a hierarchy of fermion couplings to fit the observed lepton flavor violation. Now this rings bells. TeV scale new physics with a hierarchy of fermion couplings, this is what we were wondering about in the beginning when we looked at the Higgs. So maybe there's a connection. We hence search for these leptoquarks, produced in pairs, very strong interactions. They would decay into all kinds of third-generation fermions, as the flavor physics data suggests. And then CMS here considers the sum of the transverse momenta of these final state fermions, which currently results in limits on the leptoquark mass and on the coupling strength of the leptoquark to the fermions. So this is excluded. This has an overlap with the subset of parameter space. This fits the flavor physics data, but there's more to cover. And then the point here actually is what is still to be covered can be probed completely with the LHC data that's still to come. So it's very compelling. We see here the beginning of a new interplay between flavor physics and energy frontier searches used together to pin down new physics. This was already the brief overview of our search program, which is really huge. It's a great variety of searches. I could only illustrate it here quickly with a few searches from ITLAS and CMS. There is, of course, also LHCb, which also provides sensitivity in a complementary way. Yet, for discoveries, we have the Higgs and nothing else. And this is a strong result experimentally. In particular, we now know that the simplest models of supersymmetry with TV scale masses, and they do not exist in nature. There is still, as we have also seen, a relevant parameter space to be explored. And given that fact, and given the fact that 95% of the HC data set is still to come, the conclusion here is that we still have discovery potential. So this was my message. If you allow, I would make one more statement, namely, really, it is a privilege for someone from my generation to work with this machine. And it's also a pleasure. I hope I could give you a flavor of that today. Thank you very much.